October 12th, 2025. It's been 8 days since we last had an official update on the interstellar visitor 3I Atlas, who's been gliding past our sun and shedding whispers of alien chemistry. No clear photos, no straight answers, just a story, carefully packaged, stamped comet. But is it really? Cracks in this story continue to widen, and that's why tonight we peel back the narrative and ask the one question that everyone is thinking, but no one is saying aloud. Is the official narrative the truth, or is there more going on behind the curtains? And continuing with our new multi-story format, the revelations only get darker. We'll uncover the rogue black hole drifting silently through our Milky Way, an invisible predator that could change everything we thought we knew about cosmic safety. We'll confront the colossal wound tearing open on the sun right now, one that could disrupt far more than our skies. Then, the ultimate countdown, scientists warning the universe itself may collapse in a big crunch, and the timeline is far shorter than you think. And if that weren't enough, a quiet but relentless rain of satellites is falling back to Earth every single day. 1 to 2 every day. The question is, why aren't more people talking about it? If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The arrival nobody can agree on. On July 1st, 2025, something arrived not from our sun but from the depths of interstellar space, and immediately raised eyebrows. You probably didn't hear about it. Most people didn't. But in the quiet corners of astronomy departments and research stations scattered across continents, scientists began exchanging encrypted messages, scheduling emergency conference calls, and staring at data that refused to behave the way data should. They called it 3I Atlas, catalogue designation C2025-1. The Atlas Survey telescope in Chile spotted it first, a faint smudge moving against the background stars with a trajectory that told an impossible story. This was the third confirmed interstellar object humanity had ever detected, following the famous Oumuamua in 2017 and Comet Borisov in 2019. You remember Oumuamua, perhaps? That cigar-shaped mystery that accelerated in ways gravity alone couldn't explain, that refused to outgas like a proper comet, that vanished back into the cosmic ocean before we could get a good look at it. Atlas was different. Or maybe it was the same. Nobody could quite agree. The orbital mathematics told one story clearly enough. This object was moving on a hyperbolic trajectory, meaning it wasn't bound to our solar system. It came from somewhere else, somewhere unimaginably distant, and it would leave again, disappearing back into the gulf between stars. The inbound speed clocked at roughly 60 kilometers per second, which translates to about 130,000 miles per hour if you prefer your cosmic velocities in more terrestrial units. That's fast. Faster than anything human-made has ever travelled. Faster than the solar wind. Fast enough that when you do the math backwards, when you trace that trajectory into the past, you find yourself pointing toward a region of space where no known star should have sent it. The object would reach perihelion, its closest approach to the Sun, on October 30th, 2025, passing within approximately 1.4 astronomical units of our star. For reference, 1 astronomical unit is the distance from Earth to the Sun, so Atlas would swing inside the orbit of Mars but remain comfortably beyond Earth's own path. The closest Earth approach would be about 1.8 astronomical units, far enough that even the most paranoid among us couldn't credibly claim it posed any collision risk. This wasn't melancholia. This wasn't Don't Look Up. The danger, if there was any danger at all, wasn't kinetic. But then the anomalies started piling up like evidence bags in a crime scene investigation. First came the size estimates. Initial calculations suggested Atlas might be tens of kilometers across, substantially larger than either of its interstellar predecessors. Other estimates disagreed wildly, suggesting something much smaller but with unusual, reflective properties. The uncertainty itself was strange. Modern astronomy has gotten very good at sizing up rocks in space. When estimates vary by factors of 10 or more, something about the object's surface or shape is confusing our instruments in ways that shouldn't be possible for a simple comet. Then the chemistry reports arrived, and they made no sense at all. Most comets, when they warm up approaching the sun, begin to outgas water vapour. Water ice is the primary constituent of cometary nuclei, sublimating away in beautiful tails that stretch millions of kilometres across the solar system. Atlas didn't follow this script. Spectroscopic analysis showed carbon dioxide dominating the outgassing, with water barely present. Even stranger, some observations detected high concentrations of nickel in the emissions, an element that has no business appearing in such quantities in a natural comet's exhalation. You might think astronomers would be shouting about this from the rooftops. You might imagine emergency press conferences, rushed papers, telescopes around the world pivoting to track this bizarre visitor. Some of that happened, certainly, but much of the response was muted, cautious, hedged with qualifications and maybes. Many astronomers publicly treated Atlas as simply a strange but natural comet, an outlier in the distribution but not fundamentally inexplicable. Comets are diverse, they reminded us. Each stellar system has its own chemistry. We shouldn't expect every visitor to match the composition of objects born in our own cosmic neighbourhood. And yet there were whispers, in the comment sections of preprint papers, in the quiet conversations at conferences, in the encrypted chat channels where researchers speak more freely than they do in peer-reviewed journals. Some were asking the question that dances at the edge of respectability in modern astronomy. What if Atlas wasn't entirely natural? What if we were looking at something engineered, something technological, something sent? The word probe began appearing, usually buried in conditional clauses and hypotheticals. The word alien was spoken even more quietly, often with a nervous laugh attached, a social signal that the speaker knew they were treading on dangerous ground. Careers have been damaged by taking such suggestions too seriously. Reputations have been built on dismissing them, but the numbers didn't care about reputations. The chemistry didn't care about careers. And as October approached, as Atlas drew nearer and our telescopes gathered more light from its surface, the anomalies didn't resolve themselves into comfortable explanations. If anything, they multiplied. So here we are. An object from another star system is passing through our cosmic backyard right now. As you listen to these words, it's displaying characteristics that don't quite fit any model we have for natural bodies. The data we're seeing is incomplete, scattered, sometimes contradictory, and the institutions we trust to make sense of such things are speaking in careful, measured tones that might be scientific caution or might be something else entirely. The question isn't whether Atlas is strange. Everyone agrees it's strange. The question is what kind of strange we're dealing with and who gets to decide. In the next part, we'll dig into the pulses, the spins, and the question that keeps a certain type of scientist awake at night. Is it signalling or just tumbling through the void? Part 2. Pulses in the dark. Signal or spin? Light tells stories if you know how to read it. Every photon that reaches our telescopes carries information encoded in its wavelength, its polarization, its timing. When astronomers study an object like Atlas, they're not just looking at a dot in the sky. They're analysing how that dot's brightness changes over time, constructing what's called a light curve, a graph that maps illumination against hours and days and weeks. Most comets produce messy, chaotic light curves. They tumble irregularly through space, their rotation destabilised by the uneven forces of outgassing, their surfaces pockmarked and asymmetric. The brightness variations we see are essentially noise, random fluctuations as different surface features catch the sun's light at different angles. It's the optical equivalent of white noise, predictable only in its unpredictability. Atlas didn't follow this pattern. Or rather, it did and it didn't, which might be even more unsettling. The light curve showed variations that were unusually regular, brightness changes that repeated on timescales suggesting a structured geometry, rather than chaotic tumbling. Some sections of the data displayed periodicities that made astronomers lean closer to their monitors, double-checking their calibrations, wondering if they were seeing what they thought they were seeing. The technical term is photometric periodicity, and it's exactly what you'd expect from a spacecraft deliberately rotating to control its orientation, or from a probe designed to flash patterns into the cosmos, or from any number of engineered systems that require precise control of angular momentum. It's also, to be fair, what you might see from a natural object with an unusual but still explicable shape. Perhaps a contact binary, two lobes connected by a narrow neck, spinning in a stable configuration. But then the polarization data arrived and things got weirder. Polarization measures how light waves are oriented as they travel through space. Unpolarized light vibrates in all directions perpendicular to its path of travel. Polarized light vibrates in specific planes, and the degree and direction of polarization tell us about the surface properties of whatever reflected or scattered that light. Rough surfaces depolarize light. Smooth surfaces can create strong polarization signatures. Certain geometric arrangements produce what's called negative polarization, where the polarization flips in a direction opposite to what you'd normally expect. Atlas displayed extreme negative polarization at certain angles, values that pushed the boundaries of what models predicted for any known natural surface composition. One paper described it as anomalous polarization behavior inconsistent with standard cometary dust models. Another used the phrase geometric albedo features suggesting non-random surface structure. These are the kind of careful, heavily qualified statements scientists make when they're seeing something that doesn't fit, but they're not quite ready to say what they think it might actually be. Imagine a lighthouse. The beam sweeps across the ocean at regular intervals, a precisely timed pulse that carries information to any observer with eyes to see. Now, imagine that lighthouse is tumbling through space at 60 kilometers per second, and instead of a beam of light, it's reflecting sunlight in patterns that repeat too regularly, to be random but not regularly enough to be definitively artificial. That's approximately what we're dealing with here. It might be a beacon, it might be the universe's most inconveniently shaped rock. The non-gravitational acceleration data added another layer to the puzzle. When you track an object's orbit with sufficient precision, you can detect tiny deviations from the path pure gravity would prescribe. Comets show these deviations all the time. Outgassing acts like a weak rocket engine, pushing the comet slightly off course in directions determined by where the gas is venting from the surface. For a normal comet, these forces are symmetric on average, smoothing out over time. For Atlas, the non-gravitational acceleration showed patterns that were difficult to explain with standard outgassing models. Some researchers proposed the object was what's called a dust-rich comet, a dirty rock shedding primarily solid particles rather than gas, creating forces through the radiation pressure on those particles rather than through volatile venting. This would explain some of the chemical oddities and some of the acceleration anomalies. It was a good hypothesis, a reasonable compromise between just a weird comet and possible alien probe. It didn't explain everything, but it explained enough to be respectable. And maybe that's what it was. Maybe Atlas was simply occupying a poorly explored region of the parameter space of possible cometary bodies, showing us that our models needed refinement rather than replacement. The universe is under no obligation to make sense to us. It doesn't care if we find something confusing. It just is, indifferent to our desire for clean categories and comfortable explanations. But here's what kept nagging at the researchers who studied those light curves late into the night. If you wanted to send a probe to another star system, if you wanted that probe to be detectable but not obviously technological, if you wanted to walk the line between look at me and I'm just a rock, what would you design? You'd probably create something that looked mostly natural, that could plausibly be dismissed as a comet or asteroid. But that showed just enough geometric regularity to catch the attention of anyone looking carefully. You'd want ambiguity, you'd want deniability, you'd want observers to argue among themselves about what they were seeing, and that's exactly what we got. The radio astronomers found nothing, of course. No clear periodic signals, no modulated carrier waves, no beacon transmitting across the electromagnetic spectrum in ways that would scream artificial. But absence of evidence isn't evidence of absence, particularly when we're only listening across a narrow range of frequencies, when our radio telescopes can only point at Atlas for limited windows, when the object is moving so fast that any signal would be heavily Doppler shifted and potentially unrecognizable. So we're left with ambiguity. Patterns that might be signals or might be spin, chemistry that might be alien or might just be from a very different stellar nursery than our own, acceleration that could be outgassing or could be something else. Every data point has two interpretations, sometimes three, and choosing between them requires either more information than we have or a leap of faith in one direction or another. How does this compare to the other interstellar visitors we've detected? What does the historical record tell us about objects that don't quite behave? That's where we turn next, to the shadow of Oumuamua, and what it taught us about seeing clearly. Part 3. The Oumuamua Shadow. October 19th, 2017. The Pan-STARRS telescope in Hawaii flagged an object moving through the inner solar system on an impossible trajectory. At first, astronomers assumed it was an asteroid or comet from our own Kuiper belt, perturbed inward by some gravitational interaction. But within days, as more observations accumulated, the orbital calculations converged on a disturbing conclusion. This object, soon named Oumuamua, Hawaiian for scout or messenger, had come from interstellar space. It was the first time in human history we'd confirmed an object passing through our solar system that originated elsewhere. The first time we could definitively say we were witnessing a visitor from another star, and it was bizarre. Oumuamua accelerated as it departed the solar system, a small but measurable push that couldn't be explained by gravity alone. It showed no cometary tail, no outgassing, no visible signs of the volatile ices that should sublimate when warmed by the sun. Its shape, inferred from the way its brightness changed as it tumbled, suggested something extremely elongated, perhaps 10 times longer than it was wide, a geometry virtually unknown among natural asteroids or comets. Some estimates pushed the elongation even further, suggesting a needle or cigar shape that defied conventional formation mechanisms. The scientific community responded with a cascade of papers proposing natural explanations. Maybe it was a fragment of a planet torn apart by tidal forces. Maybe it was composed of unusual materials that didn't outgaze visibly. Maybe the acceleration came from sublimating hydrogen ice, too faint to detect but sufficient to provide thrust. Maybe. Each explanation solved one problem while creating others. Each hypothesis required special pleading, invoking conditions that were possible but uncommon, convenient but unconfirmed. And then Abraham Loeb spoke up. Loeb, chair of Harvard's astronomy department, a scientist with an impressive publication record and institutional credibility to burn, suggested publicly that Oumuamua might be artificial. He proposed it could be a light sail, a thin reflective sheet pushed by radiation pressure, either a defunct piece of alien technology drifting through space, or, more provocatively, an active probe from another civilization. The scientific establishment responded with what can only be described as fury. Loeb was accused of sensationalism, of damaging astronomy's reputation, of abandoning scientific rigour for publicity. The response was so intense, so visceral, that it raised its own questions about why the idea of extraterrestrial technology provoked such defensive reactions. 2 years later, in August 2019, another interstellar visitor arrived. This one, designated 2I Borisov, behaved like a proper comet. It outgassed normally, displayed a visible tail, showed chemical compositions consistent with comets from our own solar system. The astronomy community breathed a collective sigh of relief. See, they seemed to say, interstellar objects are just like our objects. Oumuamua was weird but ultimately explicable. Everything's fine. We can return to normal, except Atlas won't let us return to normal. In some ways, Atlas resembles Oumuamua more than it resembles Borisov. Both show non-standard acceleration that challenges simple gravitational models. Both display chemical or physical properties that sit awkwardly in our taxonomies. Both occupy the borderline territory between comet and rock, neither entirely one nor entirely the other. But Atlas might be substantially larger than Oumuamua, if the size estimates are accurate. It shows that weird carbon dioxide-dominated outgassing that neither predecessor displayed. And those nickel signatures, that extreme polarization, those regular brightness variations, all push it into new territory where our comfortable analogies break down. Where Atlas departs most significantly from its cousins is in the reaction it's provoked. With Oumuamua we were surprised, unsure how to interpret what we were seeing, willing to entertain multiple possibilities. With Borisov we were relieved, eager to fit it into familiar categories. With Atlas, there's a sense that the scientific community has already decided what it wants to believe before all the evidence is in. After the Oumuamua controversy, after the accusations and counter-accusations, after watching a respected colleague get pilloried for asking uncomfortable questions, many astronomers seem to have made a collective unconscious decision to play it safe, to emphasize the natural explanations to minimize the anomalies. This is what's called an overcorrection. When you get burned touching a hot stove, you might become overly cautious around all stoves, even ones that are clearly off. When a scientific community gets burned by public speculation about alien technology, it might become overly dismissive of any evidence that points in that direction, even when the evidence deserves serious consideration. The emotional memory of the Oumuamua debate may be influencing how Atlas is being interpreted right now, creating a bias toward conventional explanations that's just as unscientific as assuming everything weird must be artificial. Loeb himself has been cataloguing the anomalies, arguing that our interpretive frameworks are systematically biased against recognizing technological signatures. He points out that we have one confirmed example of a civilization creating space-travelling objects, ourselves, and we've been launching probes beyond our solar system for decades. The idea that another civilization might do the same isn't wild speculation. It's the application of the mediocrity principle, the notion that we're not special, that what happened here probably happened elsewhere too. If we find the evidence for natural explanations insufficient, if we're invoking increasingly exotic conditions to maintain conventional interpretations, maybe we're ignoring the simplest explanation, one that's only psychologically difficult because of what it implies. Historical context matters here. Throughout the history of astronomy, we've encountered objects that seemed weird, that defied explanation, that prompted speculation about unnatural origins. Pulsars, when first discovered, were jokingly called LGMs, little green men, because the regular radio pulses seemed artificially precise. Quasars challenged our understanding of how much energy could be released from a given volume of space. Fast radio bursts still lack a completely satisfying explanation. In each case, we eventually found natural mechanisms that could produce the observations, mechanisms that were often stranger and more interesting than artificial explanations would have been. But here's the thing. Just because we found natural explanations for previous anomalies doesn't guarantee that every anomaly has a natural explanation. That's the fallacy of induction, assuming that because X was true in the past, X must be true in the future. At some point, if we ever encounter actual evidence of extraterrestrial technology, it will look anomalous. It will defy our initial models. It will prompt exactly this kind of debate. And if we've trained ourselves to always dismiss the technological hypothesis, to always find some natural mechanism no matter how contrived, we might miss the most important discovery in human history simply because we'd rather be safely wrong than uncomfortably right. So where does that leave Atlas? Tumbling through space in the gap between certainty and speculation, observed by instruments that see fragments of the truth, but never the whole picture. Which brings us to perhaps the most troubling aspect of this story, the missing data, the images that should exist but haven't been released, the gaps in the public record that might be innocent or might be something else. Let's examine what we're not seeing, and why that might matter more than what we are. Part 4, the missing data problem. Modern astronomy is a data-rich enterprise. We have telescopes in orbit, instruments on Mars, observatories scattered across every continent. When something interesting enters the inner solar system, dozens of instruments can point at it, capturing images across multiple wavelengths, building up a comprehensive picture of what we're dealing with. That's the theory anyway. The practice, particularly with Atlas, looks substantially different. The European Space Agency released a GIF from the CASSIS camera aboard the ExoMars Trace Gas Orbiter. CASSIS, designed to image the Martian surface in high resolution, was repurposed to capture Atlas during its relatively close approach to Mars. What did we get? A faint dot moving against the background of stars, a smudge barely distinguishable from noise, an image that confirmed Atlas existed and was where the orbital calculation said it should be, but revealed essentially nothing about its physical nature. For an object that was supposedly tens of kilometres across, passing within viewing range of a high-resolution camera, the lack of detail was frustrating. Either Atlas was much smaller than some estimates suggested, or it was oddly dark, or the camera wasn't pointed optimally, or some combination of factors conspired to give us the least informative image possible. Then there was the Perseverance rover, NASA's flagship Mars mission, equipped with navigation cameras that regularly scan the sky for dust devils and clouds, caught Atlas on October 4th as it appeared in the Martian sky. What did that image show? A streak, a line of light consistent with an object moving against the background stars, duration and direction matching Atlas's predicted path. Again, confirmation without revelation. We learned that Atlas was where it should be, moving as it should move, but nothing about what it actually was. These images were released, publicised, written up in press releases and news articles. They told us almost nothing, and maybe that's fine. Maybe these instruments simply weren't designed or positioned to give us better data. But here's where the story gets strange. Other instruments should have captured images, better images, and we haven't seen them. The Mars Reconnaissance Orbiter carries HiRISE, the high-resolution imaging science experiment, capable of resolving features on the Martian surface as small as 1 metre across. When an interstellar object passes relatively nearby, you'd expect HiRISE to be tasked with capturing images, multiple images, tracking the object across several orbits to build up a comprehensive data set. Where are those images? The MAVEN spacecraft, studying Mars's upper atmosphere, has optical instruments that could have contributed observations. Where's that data? The Mars Odyssey orbiter, operational since 2001, has thermal imaging capabilities that might have detected heat signatures or assessed the object's surface temperature. Has that data been released? The official explanations, when they're offered at all, invoke sensitivity limits, scheduling conflicts, instrument constraints. HiRISE was designed for planetary surfaces, not fast-moving celestial objects. MAVEN's instruments are optimized for atmospheric science, not asteroid tracking. The data processing pipeline takes time, requires calibration, needs verification before release. And oh, by the way, there was that government shutdown in early 2025 that delayed numerous NASA operations and created a backlog of data processing tasks that's still being worked through. These explanations are plausible, they're reasonable, they might even be entirely true, but they exist in a context where the absence of data creates fertile ground for alternative narratives. When people expect to see something and don't, when institutions with a history of careful documentation suddenly have gaps in their records, suspicion fills the vacuum. There's a long history of claims that space agencies have edited, delayed, or withheld anomalous images. The face on Mars, which turned out to be a mountain shaped by erosion and shadow, but was initially presented without sufficient explanation, trained a generation to mistrust NASA's image releases. Numerous conspiracy theories claim that photos from lunar missions, Mars rovers and orbital surveys have been scrubbed or airbrushed to remove evidence of structures, artifacts, or other anomalies. Most of these claims are nonsense, pattern matching on noise, seeing design in randomness. But the existence of mostly nonsense claims doesn't mean every claim is nonsense, and it doesn't mean agencies are always forthcoming with difficult data. The European Space Agency operates on a 6-month embargo for much of its raw data. Images and measurements are collected, processed internally, used by science teams, and only then released to the public archives. This is standard practice, designed to give researchers time to analyse data before releasing it to wider scrutiny. It's scientifically defensible and practically necessary. It also means there could be detailed images of Atlas sitting in ESA servers right now, images that won't be publicly available until mid-2026, images that might answer questions we're currently debating in informational darkness. This creates what might be called the data vacuum effect, when the public knows observations should exist but can't access them, when the gap between what was observed and what's been released becomes large enough to notice. Narratives rush in to fill the space. Some of those narratives are paranoid, some are conspiratorial, some posit cover-ups and secret knowledge and institutional lying. And some might actually be correct, or at least partially correct, because the absence of evidence really is evidence of absence when you expected that evidence to be present. Consider the incentive structures at play. If Atlas is just a weird comet, releasing all available data immediately carries little risk and helps advance scientific understanding. If Atlas is something more ambiguous, something that might be artificial, or that shows characteristics we can't explain, releasing that data creates problems. It invites intense scrutiny. It prompts questions the agency might not be ready to answer. It potentially reveals capabilities or limitations of our instruments that someone might prefer to keep private. It risks public panic or confusion if the implications are presented without proper context. None of this proves anything is being hidden, but it establishes that plausible motivations for selective release exist, and that the gap between what's been observed and what's been shared is larger than routine scientific caution would explain. You're being asked to trust that the institutions studying Atlas are giving you the full picture, while simultaneously being told that much of the picture won't be available for review for months or years. That's a difficult ask, particularly given the stakes. Which brings us to the question that underlies this entire investigation. Why does it matter? If Atlas is natural, we learn something interesting about interstellar chemistry and move on. If it's artificial, well, that's the biggest news in human history. But beyond those outcomes, what's really at stake in how we interpret anomalous objects? What are we really arguing about when we debate whether Atlas is a comet or something else? Let's examine belief itself and what it costs us. Part 5. Belief, skepticism, and the stakes. Ask yourself a simple question. Why does it matter whether Atlas is just a comet or something more? What changes about your life, your plans, your understanding of your place in the universe if the answer lands one way or the other? If Atlas is natural, if all those anomalies resolve into explicable chemistry and physics, we gain a rare window into the composition of another star system. We learn that planetary systems light years away can produce comets with different chemical signatures than ours, that the conditions of stellar formation vary more than we thought, that the universe is diverse in ways we're only beginning to catalogue. It's scientifically valuable, intellectually interesting, another data point in our expanding understanding of cosmic chemistry. We publish papers, we refine models, we move on to the next mystery. If Atlas is engineered, if we're actually looking at evidence of extraterrestrial technology, everything changes. This isn't hyperbole. The confirmation that intelligence exists elsewhere, that civilizations can arise and persist long enough to send probes between stars, that we're not alone in the universe, that realization would be the hinge on which human history pivots, before and after. The way we think about our significance, our future, our responsibility to the cosmos, all of it would transform overnight. But those are the clean outcomes, the binary possibilities. The harder question is what happens in between, in the territory of uncertainty where we currently live. Because right now, today, we don't know what Atlas is. We have data that points in multiple directions. We have institutions making claims we can't independently verify. We have gaps in information that might be innocent or might be suspicious. And we, the public, are being asked to decide what we believe without access to the full evidence. This is where psychological stakes enter the story. How humanity responds to potential first contact, or to even ambiguous hints thereof, reveals who we are as a species. Do we approach the unknown with curiosity or fear? Do we demand transparency from our institutions or defer to their authority? Do we allow ourselves to entertain uncomfortable possibilities, or do we retreat into comfortable certainties? The Atlas event, regardless of its ultimate explanation, is a test of our civilizational maturity. There are institutional stakes here too. Space agencies operate on public funding and political goodwill. Their budgets depend on maintaining credibility, on being seen as serious and scientific rather than speculative and sensational. If NASA or ESA announces they've found evidence of alien technology and turn out to be wrong, the reputational damage would be immense. Funding could be cut, leadership could be replaced, future missions might be cancelled. The incentive structure pushes toward caution, toward certainty, toward only making claims you can definitively defend. This is understandable. It's human. It's also a bias that could cause us to miss or dismiss genuine anomalies because acknowledging them carries professional risk. Then there's the risk of confirmation bias, the tendency to interpret new evidence as supporting what you already believe. If you want Atlas to be an alien probe, you'll emphasize the anomalies and downplay the conventional explanations. Every odd data point becomes evidence for your hypothesis. Every gap in the public record becomes proof of cover-up. You're not lying or being deliberately irrational. You're just human, filtering reality through the lens of your existing beliefs and desires. But there's an equal and opposite risk, dismissal bias, the tendency to reject uncomfortable possibilities regardless of the evidence. If you're committed to the view that Atlas must be natural, you'll emphasize the conventional explanations and downplay the anomalies. Every odd data point becomes a minor puzzle rather than a major mystery. Every gap in the record becomes innocent delay rather than suspicious withholding. You're not being dishonest. You're just protecting yourself from the discomfort of paradigm shift, from the vertigo of having your fundamental assumptions about the universe challenged. Both biases are traps. Both lead away from truth. The question is whether you can hold multiple possibilities simultaneously, weighting them according to evidence rather than preference, updating your beliefs as new data arrives rather than clinging to initial positions regardless of what the universe shows you. This connects to a deeper philosophical question. Is belief in extraterrestrial probes a modern myth, a technological age replacement for gods and angels, a projection of our hopes and fears onto the cosmos? Or is it a rational inference from the available data, an application of Bayesian reasoning suggesting that, given the age and size of the universe, given the number of potentially habitable planets, given our own existence as proof that intelligence can arise, the odds favour other civilizations existing and potentially sending emissaries into the void? The answer isn't obvious. Both positions have merit. Both can marshal evidence and logic in their defence. What's clear is that the question matters profoundly, not just for how we interpret Atlas, but for how we understand ourselves. Are we alone? If not, what does contact mean? If we're being visited or observed or simply brushed past by travellers from elsewhere, what responsibility does that place on us? These aren't abstract philosophical exercises. They're live questions with practical implications for how we allocate resources, how we plan for the future, how we conceive of humanity's role in the cosmic drama. And here's the uncomfortable truth. We're making these decisions, forming these beliefs, navigating these questions with incomplete information. The full dataset exists somewhere. Images that could resolve ambiguities, spectroscopic data that could confirm or refute hypotheses, observational records that would let us see Atlas clearly rather than through the fog of selective release and institutional caution. But we don't have access to that data. We're being asked to trust, to defer, to accept that those who know more than us are making the right calls about what to share and what to withhold. Maybe they are. Maybe the agencies studying Atlas have excellent reasons for their communication strategies. Maybe everything they're doing is scientifically sound and ethically defensible. But the structure of the situation, the asymmetry of information, the gap between what's known and what's shared, that structure itself creates the conditions for mistrust and speculation. When you treat the public as children who can't handle difficult truths, you shouldn't be surprised when the public starts assuming you're hiding something important. So we're left with uncertainty. A visitor from another star, displaying properties that challenge our models, observed by instruments whose data isn't fully available, interpreted by institutions with complex motivations. Atlas hangs in the sky, literally and metaphorically, a question mark written in rock or metal or something else entirely, and we're asked to decide what we believe about it without the information we'd need to decide rationally. But Atlas isn't the only strange thing happening in space right now. Recent discoveries, fresh cosmic news, may provide context or contrast or clues about how to interpret our interstellar visitor. In the next act, we shift focus to breaking space news, to anomalies and events that might be related or might be coincidental or might be something else entirely. Because sometimes understanding one mystery requires looking at all the other mysteries surrounding it. Sometimes the pattern only becomes visible when you step back far enough to see the whole sky. Part 6. A black hole. Without a home, imagine the most massive object you can. Neutron star, too light. Galactic core, too static. Now imagine something with the mass of several suns compressed into a region smaller than a city, warping space-time so severely that nothing, not even light, can escape its gravitational grip once the event horizon is crossed. You're imagining a black hole. Now set it adrift, cut it loose from any galaxy, any stellar system, any gravitational anchor. Send it wandering through the void between stars, a cosmic predator hunting through darkness. In 2025, astronomers confirmed observations of what they're calling a rogue black hole, a stellar mass black hole not bound to any obvious gravitational system, drifting through our galaxy like a ghost ship sailing between ports. This isn't entirely surprising in theory. Black holes form when massive stars collapse, and the galactic dynamics that govern stellar motion should occasionally fling a black hole out of its birth cluster, sending it on a lonely journey through space. What's surprising is detecting one. Black holes are famously invisible, only revealing themselves through their gravitational effects on nearby matter, or through the radiation emitted by material falling into them. A rogue black hole with no companion star, no accretion disk, no convenient matter to consume and illuminate is essentially undetectable by conventional means. The detection came through gravitational microlensing, a technique that exploits Einstein's general relativity. When a massive object passes, between us and a background star, the massive object's gravity bends the light from that star, creating a temporary brightening followed by a dimming as the alignment changes. By carefully measuring these brightness variations, astronomers can infer the mass and velocity of the intervening object. In this case, the micro-lensing signature suggested a dark, compact object with several solar masses moving through the galactic plane at velocities consistent with a stellar remnant rather than a normal star. The confirmation was significant because it validated theoretical predictions and gave us observational access to a population of objects that should be common but are rarely seen. Models suggest hundreds of millions of stellar mass black holes wander through the Milky Way, remnants of ancient supernovae, most of them completely invisible and undetectable unless they happen to pass directly in front of a background light source we're monitoring. We live in a galaxy filled with predatory gravitational wells we can't see, holes in space-time that would devour anything unfortunate enough to cross their event horizons. Now here's where it gets interesting in the context of Atlas. Could a rogue black hole have influenced our interstellar visitor's trajectory? Could gravitational interactions with such an object explain some of the orbital peculiarities we're observing? At first glance, the idea seems plausible. Black holes are gravitational powerhouses. An encounter, even a distant one, would deflect an object's path, potentially explaining the trajectory that brought Atlas into our solar system from whatever stellar neighbourhood birthed it. But the math doesn't quite work. Gravitational interactions are well understood, governed by equations we've tested to exquisite precision. For a black hole to significantly alter Atlas's trajectory without capturing it, or accelerating it to even higher velocities, would require an improbably fine-tuned encounter. Threading a needle in three-dimensional space across distances measured in light-years. Possible, yes, in the sense that nothing in physics forbids it. Likely, not particularly. The universe contains countless ways for trajectories to be perturbed without invoking rogue black holes. Yet there's something metaphorically resonant about these two anomalies existing simultaneously in our awareness. A black hole without a home and a comet without a clear origin, both wandering through space, both defying the tidy categories we prefer. Both remind us that the galaxy is more dynamic, more chaotic, more filled with drifting hazards and mysteries than the orderly diagrams in textbooks suggest. We imagine space as mostly empty, with occasional islands of matter and light. The reality is more unsettling. Space is filled with things we can't see, massive objects moving through darkness, ancient remnants of stellar death sailing between the stars we can observe. The existence of wandering black holes also raises uncomfortable questions about what else might be drifting out there. If stellar remnants can be ejected from their birth systems, what about planetary remnants? What about objects that were never gravitationally bound to begin with? What about things that were placed on trajectories deliberately rather than by random gravitational perturbations? The census of interstellar space is almost completely unknown. We see the objects that emit or reflect light toward us. Everything else, the dark matter in the colloquial rather than cosmological sense, remains invisible until it happens to pass close enough to our instruments to be detected. This connects to a larger theme running through our investigation. We're discovering that space isn't the quiet, predictable environment we thought it was. The smooth galactic dynamics we assumed, where everything orbits in orderly fashion around gravitational centres, is complicated by rogues and wanderers, by objects that don't follow the script. And if the script is wrong about black holes, if it's wrong about the number and nature of objects drifting between stars, what else might it be wrong about? The timing is curious too. Here we are in 2025 tracking an anomalous interstellar object through our solar system and simultaneously confirming the existence of rogue black holes wandering our galaxy. These discoveries aren't necessarily related. Astronomy is an active field. New findings emerge constantly. But there's something about the convergence of anomalies, the clustering of strange observations in a brief window of time, that makes pattern-seeking minds wonder if there's a connection we're not seeing. Correlation isn't causation, but it's also sometimes a clue pointing toward deeper structures we haven't recognized yet. And black holes aren't the only cosmic wound demanding our attention right now. While we've been tracking objects drifting through the galaxy, our own star has developed an injury that affects everything we're trying to observe. Let's turn our attention to the Sun and to a hole that might be interfering with how clearly we can see the truth. Part 7. The Sun's Colossal Wound. The Sun isn't smooth. We imagine it as a perfect sphere of fusion and light, consistent and predictable, the cosmic engine that powers our planetary system. The reality revealed by solar telescopes is more violent. The Sun's surface writhes with convection cells and magnetic tangles. Sunspots bloom and fade. Prominences arc thousands of kilometres into space, and occasionally the sun opens a wound. Coronal holes are exactly what they sound like, gaps in the sun's outer atmosphere where the magnetic field lines don't loop back to the surface, but instead stream outward into space. These aren't holes in the physical sense, not voids where matter is missing, but regions where the plasma is cooler and less dense than the surrounding corona, appearing dark in extreme, ultraviolet images. More importantly, they're regions where the solar wind escapes unimpeded, accelerating to speeds of up to 800 kilometers per second, carrying charged particles and magnetic fields deep into the solar system. In October 2025, solar observatories detected a massive coronal hole facing Earth, one of the largest in recent years. The hole stretched across a significant fraction of the sun's visible disk, a dark patch in the churning bright surface, like a cosmic wound that wouldn't heal. Forecasters predicted strong solar wind streams would reach Earth within days, potentially triggering geomagnetic storms, disrupting satellite operations, creating auroras at unusually low latitudes, and generally making the electromagnetic environment of near-Earth space more chaotic than normal. For most people, coronal holes are interesting primarily because they create beautiful auroras. The charged particles streaming from the sun interact with Earth's magnetic field and atmosphere, exciting atoms and molecules into emitting light, painting the sky with curtains of green and red and purple. It's a spectacular show, one of nature's most impressive light displays, and it draws photographers and tourists to high-latitude locations whenever strong solar activity is predicted. But for astronomers trying to make precise observations of faint objects, solar storms are a nightmare. The flood of charged particles interferes with radio observations, creating noise that drowns out faint signals. The magnetic field fluctuations affect spacecraft operations, potentially degrading the quality of images from orbital telescopes. Even ground-based optical telescopes can be affected as increased ionization in Earth's upper atmosphere distorts the light passing through. When the sun is actively wounded, when coronal holes are blasting plasma toward Earth, our ability to see clearly into space diminishes. Now consider the timing. Atlas reached perihelion, its closest solar approach, on October 30th, 2025. That's the moment when telescopes should have been gathering the most detailed data, when the object was brightest and closest, and most accessible to observation. And that's precisely when a massive coronal hole was facing Earth, when the solar wind was at its strongest, when the electromagnetic environment was most disrupted. Coincidence? Almost certainly. Solar activity follows its own cycles, independent of what asteroids or comets happen to be passing through. Coronal holes develop according to magnetic dynamics we don't fully control or predict. The overlap is just bad luck, an unfortunate alignment of observational windows and solar behaviour. Or is it? Here's where we have to be careful about the narratives we construct. It's very easy to see patterns where none exist, to interpret coincidences as conspiracies, to imagine that the universe or some agency within it is deliberately timing things to interfere with observation. That's almost certainly not what's happening, but the effect remains regardless of the cause. During the crucial period when Atlas was best positioned for detailed study, our instruments were operating in a degraded environment, fighting through solar noise to capture data. Any marginal signals, any subtle anomalies, any fine details that might have resolved questions about the object's nature. Those observations would have been harder to make, easier to miss, more likely to be buried in noise. The metaphor is irresistible. A hole in the sun, a wound in our star, creating a smokescreen during the very window when we needed clarity. It reads like a thriller screenplay, like something designed to maximize uncertainty. And maybe that's all it is, a coincidence that feels meaningful because humans are pattern-matching machines who see design in randomness. But it's also true that if you wanted to observe something without being clearly observed, if you wanted to pass through a stellar system while remaining ambiguous, timing your arrival during a period of high solar activity would be strategically sound. You'd benefit from the degraded observation, from the noise masking your signals, from the reduced clarity of the instruments tracking you. This is the problem with uncertainty. Once you're in it, every data point can be interpreted multiple ways. The coronal hole is just weather, solar dynamics following their own patterns. Or the coronal hole is a smokescreen, an interference pattern that benefits an object trying to remain ambiguous. Both explanations fit the facts. Neither can be definitively proven or disproven with the information available. We're left once again in the territory between knowing and speculating, and the cosmic strangeness doesn't stop with holes in the sun. While we've been watching objects drift and our star bleed plasma into space, cosmologists have been reconsidering the ultimate fate of everything. Is the universe expanding forever, or could it be heading toward a collapse? Let's examine how beliefs about cosmic destiny might be influencing how we interpret present anomalies. Part 8. The crunch clock starts ticking. The universe is expanding. Every galaxy we can see is moving away from every other galaxy, space itself stretching like the surface of an inflating balloon. This has been confirmed observational fact since Edwin Hubble's work in the 1920s, refined through decades of increasingly precise measurements. The expansion is accelerating, driven by something we call dark energy, a mysterious component of the universe that acts like anti-gravity on cosmic scales, pushing space apart faster and faster. According to the Standard Model, this expansion will continue forever, galaxies receding until they vanish beyond our cosmological horizon, stars burning out one by one, the universe growing cold and dark and empty in a heat death that takes trillions upon trillions of years. That's been the consensus. The comfortable nightmare, if you will, a fate so distant and impersonal that it barely registers as a threat. We have time, inconceivable amounts of time. Whatever else happens to humanity, to Earth, to our corner of space, the universe itself will persist for eons. Except in 2025, certain cosmological papers began questioning this assumption. New analyses of dark energy behavior, subtle patterns in cosmic microwave background data, refined models of how the universe's expansion rate has changed over time, all pointed toward a possibility that had been dismissed as unlikely. What if dark energy isn't constant? What if it's weakening, or changing character, or heading toward a phase transition that would flip the expansion into contraction? What if the universe's destiny isn't heat death, but the big crunch, a gravitational collapse that would eventually pull everything back together? Galaxies colliding, space compressing, matter and energy crushed into a singular point in a reversal of the Big Bang. The papers were tentative, heavily qualified, careful to note that the evidence was far from conclusive. The odds still favoured eternal expansion. But the possibility of contraction, once considered virtually zero, was now being assigned small but non-negligible probability. Maybe 1%. Maybe 5%. Enough that serious cosmologists had to consider it, run simulations, think about what observational signatures would confirm or refute the hypothesis. Why does this matter for our investigation of Atlas? Because cosmological narratives shape how we interpret local events. When the ultimate fate of the universe feels settled, when we're confident about the cosmic story arc, anomalies get slotted into that stable framework. This comet is weird, but the universe is stable, so the weirdness must be explicable within our existing models. But when the cosmic story itself becomes unstable, when the ending gets rewritten, suddenly everything feels less certain. If we were wrong about the universe's fate, what else might we be wrong about? If the framework itself is shifting, maybe those anomalies deserve more attention than we've been giving them. There's also a psychological dimension here. Doom narratives, predictions of cosmic endings, tend to intensify during periods of cultural anxiety or paradigm shift. Medieval Europe was obsessed with apocalypse prophecies during times of plague and social upheaval. The Cold War generated countless scenarios of nuclear winter and societal collapse. And now, in an era of climate disruption, political instability, and rapid technological change, we're seeing renewed interest in cosmic doom scenarios in endings both near and far. The Big Crunch narrative fits this pattern. It's a cosmic reset button, an ending that's also a beginning, a collapse that might lead to a new Big Bang and a new universe. It's psychologically satisfying in a way that heat death isn't. Heat death is just entropy winning, everything slowly winding down into nothing. The crunch implies purpose, cycle, the possibility that universes are born and die and are reborn in an eternal pattern. It's mythology dressed in mathematical clothing, and it appeals to something deep in human psychology that wants to believe existence has structure and meaning beyond simple thermodynamics. So when papers appear suggesting the universe might crunch rather than expand forever, they're not just presenting dry technical results. They're offering a new narrative, a different way of thinking about cosmic destiny. And that narrative primes us to interpret present events through a particular lens. If the universe itself is heading toward collapse, toward a gathering together of everything that's been flying apart, maybe interstellar visitors like Atlas aren't random wanderers, but part of some larger pattern, some cosmic choreography we don't yet understand. This is speculative territory, obviously. The connection between cosmological models and interstellar objects is tenuous at best. But narratives don't have to be logically rigorous to be psychologically powerful. When you believe the universe is on a path toward fundamental transformation, you start seeing signs of that transformation everywhere. Every anomaly becomes a herald. Every mystery becomes a clue. The framework shifts, and with it, your interpretation of everything within the framework. And here's the uncomfortable truth. Scientists are human. They're not immune to narrative influence. When the broader culture is focused on endings and transformations, when cosmological models are in flux, when the old certainties are being questioned, that atmosphere affects how researchers interpret their data, what hypotheses they consider plausible, what anomalies they think deserve investigation versus dismissal. Science isn't a pure, objective process isolated from human psychology. It's a human activity, conducted by humans with human biases and human narrative drives, and those drives inevitably influence the work. So the Big Crunch papers, regardless of their ultimate validity, change the interpretive environment. They make it easier to think big thoughts, to entertain cosmic scale possibilities, to wonder if the anomalies we're seeing are connected to larger patterns. They don't prove anything about Atlas, but they change the atmosphere in which Atlas is being interpreted, and sometimes atmosphere matters as much as evidence. But let's bring the focus back from cosmic destiny to more immediate concerns. While astronomers debate the fate of the universe, something more prosaic but equally disruptive has been happening in our orbital space. Satellites are falling, regularly, quietly, and their rain of fire might be masking something important. Part 9. Starlink's quiet rain of fire. Every day, somewhere above your head, a satellite dies. Not metaphorically. Literally. Metal and silicon and solar panels heating to thousands of degrees as they slam into Earth's atmosphere, ablating away, breaking apart, raining down as microscopic debris or occasionally larger fragments that survive to impact the surface. A Smithsonian astrophysicist recently estimated that 1 to 2 Starlink satellites burn up or fall back to Earth daily. Not monthly. Daily. That's hundreds of objects per year from a single mega constellation, vaporizing as they descend. The reason is simple physics. Low Earth orbit isn't empty. There's residual atmosphere even at altitudes of several hundred kilometers, enough to create tiny amounts of drag on satellites. Over time, that drag slows the satellites, lowering their orbits, until eventually they dip into denser atmosphere and can't maintain altitude anymore. Orbital decay is inevitable. Every satellite launched will eventually fall unless constantly boosted to maintain its orbit. For small satellites without substantial fuel reserves, the operational lifetime might be only a few years before atmospheric drag wins and they begin their final descent. Starlink, SpaceX's mega constellation designed to provide global internet coverage, consists of thousands of satellites in low orbit. The plan calls for tens of thousands eventually, a network so dense that from any point on Earth, multiple satellites are visible above the horizon. This requires operating in low orbits where atmospheric drag is significant, which means satellites must be regularly replaced as they decay and burn up. Hence, the daily rain of fire, a steady stream of dying hardware vaporizing over our heads, mostly unnoticed because the individual events are too small and too common to make news. But here's what this does to the observational environment. It adds clutter. Thousands of satellites reflecting sunlight, interfering with telescope observations, creating streaks across astronomical images that have to be digitally removed. It increases false positives, objects that appear briefly in sky surveys, but turn out to be satellites or satellite debris rather than asteroids or comets. It makes the already difficult task of tracking small objects through space even harder, because you have to distinguish genuine celestial phenomena from the growing cloud of human-made hardware cluttering near Earth space. For observers trying to study something like Atlas, this matters. When you're analysing faint objects, when you're looking for subtle variations in brightness or trajectory, When you're trying to confirm whether an observation is real or artifact, the presence of thousands of artificial objects in your field of view complicates everything. Every mysterious signal could be a satellite. Every unexplained flash could be debris catching sunlight at an unusual angle. The noise floor rises, and with it, the difficulty of extracting genuine signals from background. There's also a more speculative possibility worth considering. Can the proliferation of satellite activity provide cover for detecting or masking other anomalies? If you wanted to observe Earth without being clearly identified, if you wanted to pass through near-Earth space while maintaining plausible deniability, blending in with the thousands of artificial objects already present would be strategically sound. Every telescope that sees you could reasonably assume you're just another satellite, just more orbital debris, just part of the growing clutter that everyone's learned to filter out. The camouflage isn't deliberate on your part. It's provided by humanity's own technological infrastructure, by the constellation of hardware we've surrounded ourselves with. This connects to a broader theme about signal and noise, about how increasing complexity makes it harder to see clearly. The more satellites we launch, the more difficult astronomy becomes. The more space junk accumulates in orbit, the harder it is to distinguish significant observations from insignificant ones. We're creating our own fog, surrounding ourselves with a technological haze that obscures the very cosmos we're trying to study, and anything that wants to remain hidden or ambiguous or unnoticed benefits from that haze. The irony is thick. We launch satellites to improve communication and observation, to give us better tools for studying the universe, but in doing so, we degrade the environment those observations happen in, making it harder to see faint objects, harder to track anomalies, harder to know whether what we're detecting is significant, or just another piece of falling hardware catching sunlight as it burns. Progress creates its own obstacles. The better our technology gets, the more that technology interferes with itself. And there's no easy solution. The satellites serve purposes people value. Internet access, weather monitoring, communications infrastructure, all depend on the orbital constellation. Arguing to reduce the number of satellites means arguing to give up capabilities and services that millions of people rely on. So the constellation will grow, the clutter will increase, and the observational environment will continue to degrade. That's the trajectory we're on, and barring some major policy shift or technological breakthrough, it's the trajectory we'll stay on. Which brings us to perhaps the most puzzling aspect of the Atlas story: the silence, the gaps in communication, the sense that institutions which should be sharing information are holding back. Why are the agencies so quiet when odd things appear? What's the logic, or the fear, behind selective disclosure? Let's examine the silence itself and what it might tell us. Part 10. The silence before disclosure. Silence is a kind of information. When you expect to hear something and don't, when institutions that normally communicate regularly suddenly go quiet, when the absence of statements becomes more noticeable than the presence of them, you're receiving a signal even if it's a negative one. The silence around Atlas, the gaps between observations and announcements, the careful vetting of every public release, all of it communicates something even if we're not sure exactly what. Space agencies operate under constraints most people don't think about. Every image released to the public has to be reviewed, calibrated, verified. Every statement about observations has to be precise, defensible, unlikely to be contradicted by future data. This isn't censorship or conspiracy. It's the normal caution of institutions that understand their credibility depends on accuracy. If NASA announces a discovery that later turns out to be instrumental error or misinterpretation, the damage to their reputation can be severe and long-lasting. So they check, they double-check, they wait until they're confident before saying anything publicly. This creates a temporal gap, a delay between observation and announcement that's usually measured in weeks or months. For routine observations, this barely matters. So what if the press release about some distant galaxy comes 6 months after the telescope captured the image? The galaxy isn't going anywhere. But for time-sensitive events, for objects passing through our solar system on schedules measured in days and weeks, that delay becomes significant. By the time the agency is ready to make a statement, the event has often passed, the object has moved on, and the public is left wondering why they weren't informed earlier. The pattern is visible across multiple recent events. When new exoplanets are discovered through gravitational wave detection or transit methods, Months often pass before the discovery is announced. When interesting signals are detected by radio telescopes, extensive verification happens internally before anyone outside the research team is informed. When orbital missions capture unusual images, those images go through processing and analysis pipelines that can take a year or more before public release. This is standard operating procedure, not specific to Atlas or any particular mission, but standard procedure feels different when the observation might be extraordinary, when the delay affects data that could answer fundamental questions about our place in the universe, when the gap between seeing and sharing creates space for speculation and alternative narratives. The routine caution starts looking like something else. It starts looking like deliberate withholding, like information control, like an institution deciding what the public gets to know and when. This is where institutional incentives create problems. Agencies want to control their narratives. They want to make announcements on their own schedule, in their own words, with their own framing. Leaks are bad. Premature releases are bad. Speculation before verification is bad. All of this makes sense from the agency's perspective. But from the public's perspective, it looks like secrecy. It looks like decisions being made behind closed doors about what information is suitable for general consumption. And that appearance, regardless of whether it reflects reality, damages trust. There's historical precedent for agencies delaying or initially withholding anomalous findings. The famous face on Mars captured by Viking orbiter in 1976 was initially presented in a press release that emphasized its artificial appearance before later releases provided context about how lighting and resolution affected interpretation. The WOW signal, detected in 1977 by SETI researchers, wasn't publicly discussed in detail for years despite being one of the most intriguing radio observations ever made. The dimming of Tabby's star, which some speculated might indicate an alien megastructure, was known to researchers well before it became public knowledge through data release. In each case, there were reasonable explanations for the delay. Scientists wanted to rule out instrumental error. They wanted to gather more data. They wanted to avoid making claims they couldn't defend. But the effect was the same. The public learned about potentially significant observations long after they occurred, through channels that felt more like PR management than transparent scientific communication. And each instance reinforced the sense that institutions were gatekeeping information, deciding what questions were acceptable to ask publicly and which should remain in private discussions among credentialed experts. Apply this pattern to Atlas. The object was discovered in July. It's now late October. We've seen a handful of images, mostly showing faint dots or streaks. We've read press releases emphasizing the natural comet explanation, downplaying anomalies, reassuring us that everything is normal and expected. We haven't seen high-resolution images from instruments that should have captured them. We haven't had access to the raw spectroscopic data that would let independent researchers verify the chemical claims. We're being asked to trust that the institutions studying Atlas are telling us everything important, while simultaneously being aware that their history suggests they often don't. This creates what might be called the silence window, the gap between observation and disclosure where narrative management happens. During this window, the agency controls the story. They decide what gets emphasized and what gets buried in technical appendices. They frame the discovery in language that shapes how the public interprets it. And they do all of this behind closed doors, in internal meetings and peer review processes that the public never sees. By the time we get the official story, the narrative has already been constructed, the interpretation decided, the acceptable range of speculation defined. Is this conspiracy? Not in the sense of deliberate malicious cover-up, but it is information, control, narrative management, institutional self-protection, and it creates the conditions where conspiracy theories flourish, because when people know they're not getting the full story, they fill the gaps with their own narratives, often more dramatic and less plausible than the truth would be if it were simply shared openly. Atlas sits at the centre of multiple weird signals, multiple cosmic anomalies that may or may not be related, rogue black holes wandering the galaxy, holes in the sun disrupting observations, cosmological models in flux, satellites falling like rain. Each of these could be independent, unconnected developments, or they could be pieces of a larger pattern we're not seeing because the data is scattered, the release is delayed, the narrative fragmented by institutional caution and communication strategies. What we know is that an object from another star system is passing through ours right now. displaying properties that challenge our models, and the institutions studying it are being careful about what they share and when. The silence might mean nothing, or it might mean everything. We won't know until the window closes, until the data is finally released, until we can see for ourselves what Atlas actually is. Until then, we're left with gaps and guesses, watching the sky and wondering what's being seen but not shared. And speaking of the sky, let's shift our attention to the calendar itself. Because while all this strangeness unfolds, celestial events march forward on schedules set by orbital mechanics and cosmic timing. These events, these spectacles, might be distractions or they might be opportunities. They might hide what we need to see or reveal what's been hidden. Either way, they're coming. Mark your calendars. The show is about to begin. Part 11. The cold moon rises December 4th. The moon has many names, inherited from cultures that tracked its phases as calendar and clock. The full cold moon rises on December 4th, 2025, the name given by colonial Americans following indigenous traditions that associated this particular full moon with the onset of deep winter, with cold nights and frozen ground, with the year drawing toward its darkest point before the solstice promises eventual return of light. There's something primal about full moons. They've triggered human behaviour for as long as humans have existed, marking times for hunting, for planting, for ritual and celebration. Modern people like to think we're beyond such influences, that electric lights and digital calendars have freed us from lunar tyranny. But hospital emergency rooms still report increased activity during full moons. Police departments note changes in call patterns. Sleep studies show measurable effects on human circadian rhythms even when subjects can't see the moon. We're still animals, still influenced by the ancient rhythms our ancestors evolved under, even if we pretend otherwise. The cold moon will be visible globally, weather permitting, rising in the east as the sun sets in the west, climbing to its highest point around midnight, illuminating the landscape with that peculiar colourless brightness that's bright enough to read by, but not quite bright enough to see colour. It's a liminal light, caught between day and night, making the familiar world strange and the strange world visible. From a strictly astronomical perspective, this full moon is unremarkable. It's not a supermoon, not unusually close or large or bright. It's just the moon being the moon, completing another orbit, reflecting another face of sunlight toward Earth. But symbolically, culturally, psychologically, it matters. People will go outside to look at it. Photographers will capture it rising over landscapes and cityscapes. Social media will fill with moon images, each one slightly different, each one attempting to capture the uncapturable feeling of standing under that light and feeling small and connected and ancient all at once. Now here's a speculative overlay. What if anomalies like Atlas are timed, deliberately or coincidentally, to pass when public attention is fixed elsewhere? The full moon is a natural spotlight, a celestial event that draws millions of eyes upward. When people are looking at the moon, they're not looking at other things. When telescopes are pointed at the moon, or dealing with its brightness drowning out faint objects, they're not tracking anomalies in other parts of the sky. The moon, in effect, creates a blind spot, a moment of collective attention that could mask other events happening simultaneously. This isn't to suggest some cosmic conspiracy where alien visitors coordinate their arrivals with lunar phases. That's absurd. But it is to note that when human attention is concentrated in one direction, opportunities arise in other directions. Magicians understand this principle. Misdirection is the core of the craft. Get the audience looking at your right hand, they'll miss what your left hand is doing. Get the audience looking at the moon, they'll miss what's moving in the darker sky beyond it. The cold moon also carries symbolic weight that affects how we interpret events around its timing. Cold suggests closure, dormancy, the end of a cycle. December is when things die back, when growth stops, when the world turns inward. If strange events cluster around this timing, if disclosures or discoveries happen in early December, they'll be interpreted through that symbolic lens, endings rather than beginnings, closure rather than opening. The narrative frame shifts based on when things are revealed, even if the timing is purely coincidental. And maybe it is purely coincidental. Maybe lunar phases and interstellar visitors have nothing to do with each other. Maybe the cold moon is just the moon, and Atlas is just passing through, and any connection between them is pattern matching on randomness, But humans are storytelling animals. We can't help but see narratives in events, connections in coincidences, meaning in timing. The moon rises, the visitor passes, and somewhere in the overlap we construct a story that makes sense to us, even if it doesn't make sense to the universe. The important thing is to notice what you're noticing. When the cold moon rises, when your attention goes skyward, ask yourself what else is happening. What other objects are moving through space? What data is being released or withheld? What announcements are being made or delayed? The moon is beautiful, worth watching, worth photographing and celebrating. But don't let its beauty blind you to everything else the sky contains. Sometimes spectacle is just spectacle, and sometimes it's cover for something you'd otherwise notice. Speaking of spectacle, the cold moon is just the opening act. A supermoon is coming, bigger and brighter, guaranteed to dominate headlines and social feeds. Let's examine how the biggest lunar show of 2025 might be shaping what we see and what we miss. Part 12. The supermoon of 2025. Early November. A supermoon sounds dramatic, like something out of comic books or disaster movies. The reality is more subtle but still genuinely impressive. A supermoon occurs when the full moon coincides with perigee, the point in the moon's elliptical orbit where it passes closest to Earth. The moon's orbit isn't circular, it's an ellipse, which means sometimes the moon is about 50,000 kilometres farther from Earth than at other times. When the full moon happens at perigee, it appears about 14% larger and 30% brighter than when it's at apogee, the farthest point. That's enough to be visually noticeable if you're paying attention, especially when the supermoon rises near the horizon, where atmospheric effects can make it look even larger through an optical illusion. The biggest supermoon of 2025 occurs in early November, either the 3rd or 4th depending on how you measure the exact moment of perigee versus the moment of full illumination. For casual observers, the distinction doesn't matter. What matters is that for several nights, the moon will dominate the night sky, bright enough to cast strong shadows, beautiful enough to stop people in their tracks, attention-grabbing enough to become a cultural moment rather than just an astronomical event. And that's where it gets interesting from our perspective. Supermoons generate massive public engagement. They're accessible astronomy, requiring no equipment beyond eyes and curiosity. News outlets cover them. Weather forecasters mention them. Social media explodes with supermoon photos taken from every possible location and angle. For a few nights, millions of people who normally never think about celestial mechanics become amateur moon watchers, stepping outside to look up, sharing what they see, participating in a collective, astronomical experience. This is wonderful. Anything that gets people interested in space, that makes them look up and wonder, that connects them to the cosmos beyond their immediate concerns, that's a net positive for human civilization. But it's also a massive redirection of attention. When everyone's looking at the moon, when telescopes are dealing with its brightness, when the cultural conversation is dominated by supermoon imagery, other things can pass relatively unnoticed. Atlas's closest Earth approach happens in late October, just before the November supermoon. The timing means that as Atlas is moving through the most observable part of its trajectory, public attention is about to be captured by a lunar spectacle. Professional astronomers will still track Atlas, of course. They're not distracted by pretty moons, but public attention, media coverage, the broader conversation about what's happening in space, all of that shifts toward the more accessible, more visually dramatic event. Atlas becomes background noise, if it's mentioned at all, overshadowed by the supermoon's mainstream appeal. There's a historical pattern here worth noting. Major announcements sometimes get released when public attention is elsewhere. Governments announce unpopular policies on Friday afternoons before holiday weekends. Corporations release bad financial news after markets close. It's not necessarily conspiracy. It's just strategic communication, choosing timing that minimizes negative attention or allows the message to be processed without immediate intense scrutiny. Could the same principle apply to space anomalies? Could timing disclosures or non-disclosures around major celestial events be a deliberate strategy for managing public reaction? Maybe. Or maybe the timing is genuinely coincidental, the result of orbital mechanics and observational windows having nothing to do with communication strategy. But the effect remains. When the supermoon dominates the cultural conversation about space, anomalies like Atlas fade into background. Questions that might be asked loudly in a quieter news environment get asked softly or not at all, drowned out by supermoon excitement. And here's the psychological dimension. Supermoons are comforting in a strange way. They're predictable, expected, part of the regular rhythm of celestial mechanics. They remind us that some things about the universe are stable, that orbital dynamics follow comprehensible rules, that we can predict and prepare for these events with perfect accuracy. In a time of cosmic uncertainty, when interstellar visitors and rogue black holes and cosmological doom scenarios are circulating through scientific discourse, the supermoon offers reassurance. Look, it says, the universe still works the way you learned in school. The moon still orbits Earth. Perigee and apogee still happen on schedule. Not everything is strange. That reassurance, that return to the familiar, might be exactly what people need, psychologically, or it might be what prevents them from grappling with genuinely strange developments. When you're offered comfort, when spectacle provides an easy focus point, it's tempting to accept that and ignore the harder, more unsettling questions lurking just outside the spotlight's reach. The supermoon is beautiful. But beauty can be a trap, something that keeps you looking in one direction while other directions remain unexplored. So when the supermoon rises in November, when the sky is dominated by that enlarged, brightened disk, remember to look around it. Check what else is visible. Ask what data is being released or held back. Notice whether announcements happen during the supermoon window or are strategically delayed until after the spectacle passes. The moon deserves your attention, but it shouldn't monopolize it. The sky is larger than the brightest object within it, and sometimes the most important things are happening in the darker spaces we'd rather not examine. Speaking of things streaking through darkness, the supermoon isn't the only celestial show scheduled for the coming months. Meteor showers are approaching, annual events that paint the sky with fire and have their own ways of capturing attention and perhaps concealing what we should be noticing. Let's turn to the southern Taurids and what happens when the sky fills with streaks of light. Part 13, Fire in the Sky, the Southern Taurids. Every year in early November, Earth's orbit carries us through a stream of debris left behind by Comet Encke, a short-period comet that swings through the inner solar system every 3.3 years. The debris forms a river of particles spread along the comet's orbital path, and when Earth intersects that river, the particles slam into our atmosphere at speeds of around 30 kilometers per second. Friction heats them to incandescence. They vaporize in brilliant streaks. We call it a meteor shower, specifically the southern Taurids, named because the meteors appear to radiate from the constellation Taurus. The southern Taurids aren't the most spectacular meteor shower. Peak rates are typically only 5 to 10 meteors per hour, modest compared to showers like the Perseids or Geminids that can produce dozens or even hundreds of meteors per hour during their peaks. But the Taurids have a reputation among meteor enthusiasts for producing fireballs, unusually bright meteors that can briefly outshine even the brightest stars, occasionally leaving persistent trains of glowing ionized gas that linger for seconds after the meteor itself has vanished. The shower is active from late September through late November, with peak activity typically occurring in early November, overlapping with that supermoon window we just discussed. So during the same period when the moon is unusually bright and public attention is skyward, the sky is also being regularly streaked by meteors, natural fireworks that add to the spectacle and to the overall sense that a lot is happening above our heads. From one perspective, this is pure coincidence. Earth's orbit is fixed. Comet Encke's debris stream is where it is. The moon's perigee happens when it happens. These are independent phenomena, determined by gravitational mechanics that care nothing for human observation or interpretation. The timing overlap is just the universe being busy in multiple ways simultaneously. From another perspective, the overlap creates noise. When you're trying to track specific objects through space, when you're looking for anomalies or unusual trajectories, a sky full of meteors complicates the task. Every streak of light has to be identified. Is it a Taurid meteor? Is it a satellite? Is it space debris? Is it something else? The more natural phenomena are occurring, the harder it becomes to distinguish signal from noise, the genuine anomaly from the expected event. And here's a speculative question worth considering. Could fragments from interstellar objects be misclassified as meteors? Atlas is outgassing, shedding material as it passes through the solar system. That material forms a tail, a cloud of particles following the comet's trajectory. If Earth happened to pass through that particle stream, if pieces of interstellar matter entered our atmosphere, would we recognise them as distinct from the annual meteor showers we expect? Or would we assume they were just part of the Taurids, just more debris from Comet Encke, and never investigate further? The chemistry should reveal the difference. Meteor spectroscopy can identify composition, and material from an interstellar object should show chemical signatures distinct from solar system comets. But that assumes someone captures a spectrum of the specific meteor in question, that the observation happens during the brief seconds while the meteor is visible, that someone notices something unusual enough to warrant detailed analysis. For the vast majority of meteors, we see a streak, maybe photograph it, and move on. The detailed spectroscopy happens only for the most interesting or well-observed cases. This creates a pattern blending effect. High meteor activity provides cover, a background of expected events that might mask unexpected ones. If you wanted to study Earth without being clearly identified, if you were shedding material that might enter Earth's atmosphere, timing that process to coincide with a major meteor shower would be strategically sound. Your debris gets mixed with expected debris. Your signals get lost in expected signals. And human observers, seeing what they expect to see, classify everything as part of the known phenomenon without looking closer. Again, this is speculation. There's no evidence that Atlas fragments are entering Earth's atmosphere. There's no proof that anything unusual is hiding among the Taurids. But the structural possibility exists, the theoretical window where misidentification could occur, and that window is worth noting because it affects how confidently we can claim to know what we're observing. There's also the simple fact that meteor showers draw eyes upward. Like the supermoon, like any celestial spectacle, they focus attention in specific directions at specific times. When people are outside watching for Taurid fireballs, they're engaged with the sky in ways they normally aren't. They're noticing things, pointing at things, photographing things, but their attention is directed toward the meteors, toward the expected show. Other objects moving through the sky might be visible but unnoticed, background to the foreground performance. The Taurids also carry a certain mythology in astronomical circles. Some researchers have suggested that the Taurid complex, the broad stream of debris associated with Comet Encke, might contain larger fragments, kilometre-sized rocks that pose potential impact hazards to Earth. These claims are controversial and not widely accepted, but they add an undercurrent of threat to what's otherwise a beautiful annual event. When you watch Taurid meteors, you're watching small particles that pose no danger, but in the back of your mind might be the question of whether something larger is out there, hidden in the same debris stream, potentially on a collision course. Atlas isn't part of the Taurid complex. Its origin is interstellar, completely unrelated to Comet Encke. But the psychological association, the connection between things in the sky and potential threat, creates a framework where anomalous objects get interpreted through a lens of danger. The Taurids remind us that space contains hazards. Atlas, arriving from interstellar space with unusual properties, gets slotted into that hazard category even though it poses no collision risk. The narratives blend, not because they're factually related, but because they activate similar psychological responses. So when the southern Taurids peak in early November, when the sky fills with streaks and fireballs, pay attention not just to the meteors but to what else might be moving. Notice whether unusual objects get reported and dismissed. Ask whether the pattern blending is innocent or convenient. The Taurids are worth watching. They're a genuine natural wonder, a reminder that we live inside a dynamic system where matter is constantly in motion. But don't let the expected show blind you to unexpected performances happening in other parts of the sky. And the Taurids are just the beginning. More meteor showers are coming, a cascade of celestial fireworks that will light up the sky through November and December. Let's examine how this clustering of spectacles might be shaping what we see and what remains hidden in the spaces between the streaks. Part 14. The Leonids, Geminids and Ursids, a cascade of showers. The sky in late 2025 is busy, not just with Atlas, not just with supermoons and coronal holes, but with the regular programming of meteor showers, 3 major displays arriving in quick succession like a coordinated performance scheduled by the universe itself. The Leonids arrive on November 17th and 18th, debris from Comet Tempel-Tuttle creating meteors that appear to radiate from the constellation Leo. The Leonids are famous for occasionally producing meteor storms, events where thousands of meteors per hour paint the sky, though those storms happen only during specific years when Earth passes through particularly dense regions of the debris stream. 2025 isn't a storm year. The Leonids will be modest, maybe 10 to 15 meteors per hour at peak, visible in the pre-dawn hours when Leo is highest in the sky. Then come the Geminids on December 13th and 14th, generally considered the most reliable and impressive meteor shower of the year. The Geminids are unusual because they originate not from a comet but from an asteroid, 3200 Phaethon, a rock that may be an extinct comet that's shed all its volatiles and now consists only of the rocky core. The Geminids can produce up to 120 meteors per hour during peak activity, bright multicoloured streaks visible from anywhere on Earth, weather permitting. They're a reliably spectacular show, the kind of event that gets news coverage and draws people outside even in December cold. Finally, the Ursids on December 21st and 22nd, radiating from the constellation Ursa Minor, debris from Comet Tuttle. The Ursids are typically sparse, maybe 5 to 10 meteors per hour, and they suffer from unfortunate timing, peaking around the winter solstice when nights are longest in the northern hemisphere, but weather is often poor. They're the quiet closing act of the year's meteor calendar, less impressive than the Geminids but still a regular feature of the December sky. 3 major showers across 5 weeks, overlapping with Atlas's passage through the inner solar system, overlapping with the supermoon, overlapping with increased solar activity from that coronal hole. If you were designing a period of maximum celestial business, maximum sky activity, maximum reasons for people and instruments to be looking upward, you couldn't schedule it much better than this. The universe has delivered a spectacular autumn and early winter, a season of cosmic displays that will keep astronomers and casual observers engaged for months. And here's where the pattern raises questions. When meteor showers cluster, when the sky is regularly streaked with expected phenomena, the observational environment becomes more complex. Every unknown object has to be distinguished from the known background. Every anomalous observation competes for attention with spectacular but explicable events. The meteors are beautiful, worth watching, scientifically interesting in their own right, but they are also noise from the perspective of tracking other objects. They're a baseline of activity that other signals have to rise above to be noticed. Could interstellar fragments, dust clouds following Atlas's trajectory, particles shed during its passage through our solar system, could any of these coincide with the regular meteor showers? Could material from another star system be entering Earth's atmosphere right now, burning up alongside Leonid or Geminid meteors, misclassified or simply unnoticed because we expect to see meteors during these periods and we see what we expect? The chemistry would reveal the truth if we looked closely enough. But we're not capturing detailed spectra of every meteor. We're not analysing every streak. The vast majority of meteors are observed visually, photographed perhaps, and that's it. Only a tiny fraction get the detailed scientific attention that would reveal unusual composition. So if interstellar material is mixed in with solar system material, if anomalous particles are hiding among expected particles, the odds of detection are low unless something is obviously different, spectacularly strange, impossible to misclassify. There's also a human element here. When celestial events are baked into the calendar, when they're expected and anticipated and normalised, they become part of the background reality. The Geminids happen every December. The Leonids happen every November. These are facts, regular occurrences as predictable as seasons. They're not mysteries, they're not anomalies, they're cosmic infrastructure, the regular rhythm of Earth's journey around the Sun carrying us through debris streams left by various comets and asteroids. This normalisation is useful. It allows us to predict and prepare for events. It lets us schedule observations and public outreach. It turns chaotic cosmic phenomena into comprehensible patterns. But it also creates blind spots. When something is normalised, we stop questioning it. We stop looking at it with fresh eyes. We classify and file and move on. And if something genuinely unusual is hiding within the normalised pattern, we might miss it entirely because we've trained ourselves not to look too closely at events we think we understand. The clustering of these showers around Atlas's passage could be pure coincidence. Orbital mechanics care nothing for our narratives. Earth's path through various debris streams is determined by gravitational laws that operate independently of what interstellar objects happen to be passing through simultaneously. There's no reason to think the timing is coordinated or meaningful, except timing creates context. When major news stories break during periods of distraction, they get less attention. When significant developments happen while the public is focused elsewhere, they can be overlooked or underplayed. The same principle might apply cosmically. When the sky's full of expected spectacles, when meteor showers and supermoons and other regular phenomena dominate attention, anomalies can pass with less scrutiny than they'd receive during quieter periods. This isn't necessarily deliberate. It doesn't require conspiracy or coordination. It's just the natural result of attention being finite, of there being only so many hours in the night, only so many telescopes to point at the sky, only so much processing capacity for data analysis. When there's a lot happening, not everything gets equal attention. Priorities get set, resources get allocated, and some things, potentially important things, might get relegated to lower priority simply because they're competing with more immediate or more spectacular events. So as the Leonids streak and the Geminids blaze and the Ursids close out the year, remember that you're watching a curated show. Not curated by any human hand, but curated by the limitations of attention and observation. What you see is what's brightest, most obvious, most expected. What you don't see might be more important, hidden in the darker spaces between the meteors, moving through the sky while your eyes track the streaks. Which brings us to the final question we've been circling throughout this investigation. Are all these cosmic events, these moons and meteors and holes and anomalies, are they just timing? Just coincidence? Just the universe being busy in multiple unrelated ways simultaneously? Or is there something larger at play? Some pattern we're not recognizing because we're too close to see it clearly? Let's step back and examine the calendar itself and ask whether we're living through a countdown to something we haven't identified yet. Part 15. Calendar or Countdown. Look at what we've assembled. An interstellar object with anomalous properties passing through our solar system. A rogue black hole wandering our galaxy. A massive coronal hole disrupting solar observations. Cosmological papers suggesting the universe might crunch rather than expand forever. Satellites falling daily, creating observational noise. A supermoon capturing public attention. 3 major meteor showers clustered across 5 weeks. The cold moon rising with all its symbolic weight of endings and closure. Each of these taken individually is explicable, natural, expected or at least not unexpected. The universe is large and busy and strange things happen regularly. Finding multiple strange things happening simultaneously shouldn't surprise us. The sample space is huge. The number of potentially interesting cosmic events is vast. Some overlap is inevitable. But there's something about the convergence that nags at pattern-seeking minds. These aren't just random events scattered across time. They're clustered, concentrated in a narrow window from late October through December 2025. And they all, in various ways, affect either our ability to observe clearly or our attention as observers. The coronal hole degrades instruments. The supermoon captures attention. The meteor showers create background, noise. The satellites add clutter. Atlas moves through it all, ambiguous and anomalous, observed but not clearly, questioned but not answered. So here are 3 interpretive frames, 3 ways of understanding what we're witnessing. First, pure coincidence. The universe doesn't care about human observation or interpretation. These events are independent phenomena that happen to overlap because that's what random distributions sometimes produce. Clusters occur in randomness. Coincidences happen. Seeing pattern here is just apophenia. The human tendency to perceive meaningful connections in meaningless noise. This is the safest interpretation. The one that requires no special pleading, no exotic hypotheses. It's probably right. Second frame, narrative camouflage. Not conspiracy, not coordination, but a structural condition where genuine anomalies benefit from occurring during periods of high noise and distraction. If Atlas is something unusual, something that would attract intense scrutiny during quieter periods, its passage during a season of spectacles provides natural cover. Not because anyone planned it that way, but because the busy observational environment makes it harder to focus, harder to confirm, easier to dismiss or defer for later analysis. Under this frame, the timing doesn't have to be deliberate to be consequential. The effect exists regardless of intent. Third frame, cosmic choreography. This is the most speculative, the hardest to defend, but worth articulating. What if these events are connected at a level we don't recognise? What if Atlas is part of something larger, a phenomenon or process that affects multiple aspects of the cosmic environment simultaneously. We've been assuming these are independent variables, separate events happening in parallel, but what if they're coupled somehow? What if rogue black holes and interstellar visitors and solar activity, and even meteor stream distributions are linked through mechanisms we haven't discovered yet? Under this frame, we're not seeing coincidence. We're seeing a pattern whose logic remains hidden because we lack the theoretical framework to recognize it. Each frame has strengths and weaknesses. The coincidence frame is parsimonious but potentially dismissive of genuine anomalies. The camouflage frame acknowledges structural effects without requiring intent but might overinterpret noise. The choreography frame is intellectually exciting but demands evidence we don't have and probably won't get. Choosing between them requires weighing not just data but philosophical commitments about how the universe works, whether it contains hidden patterns, whether coincidence is always just coincidence. What's clear is that the celestial calendar for late 2025 has delivered an unusually rich collection of events. Whether that richness is random or meaningful, whether the timing aids or hinders discovery, whether we're living through cosmic business as usual or something more significant, these questions can't be definitively answered with the information available. We're left in uncertainty, watching the sky, tracking the schedule, wondering if the calendar is counting time or counting down to something. And here's the final uncomfortable thought. Maybe the question itself is the point. Maybe what matters isn't whether Atlas is natural or artificial, whether the timing is coincidental or choreographed, whether we're witnessing something extraordinary or just misinterpreting the ordinary through the lens of our hopes and fears. Maybe what matters is that we're asking these questions at all, that we're looking up, that we're grappling with uncertainty rather than retreating into false certainty. The narrative around Atlas, the story we're constructing about what it is and what it means, that narrative says as much about us as it does about the object itself. It reveals how we handle ambiguity, whether we rush to conclusions or sit with not knowing, whether we trust institutions or question them, whether we're willing to entertain uncomfortable possibilities, or whether we need the universe to behave in expected ways for our psychological comfort. So look up, watch the cold moon rise, count the meteors as they streak. Notice the supermoon's brightness and the darkness around it. Track Atlas as it passes through our solar system and disappears back into the interstellar void. But also look inward. Notice what you want to believe and why. Notice what makes you uncomfortable and what that discomfort protects you from feeling. Notice the stories you tell yourself about what's happening in the sky and recognize them as stories, human constructions layered over phenomena that exist independent of our interpretations. The calendar continues. The countdown, if there is a countdown, proceeds according to schedules we don't control. Events will unfold, data will eventually be released or remain withheld, questions will be answered or will transform into new questions, and we'll be here, watching, wondering, constructing narratives because that's what humans do when faced with mystery. Who wrote this schedule, the clustering of cosmic events across these specific months? Did anyone write it? Or is that question itself a category error, an attempt to impose authorship on processes that simply are? The universe doesn't write, it doesn't plan, it unfolds according to laws we partially understand, producing patterns that sometimes look designed but might just be the inevitable result of complexity iterating across vast timescales. Or maybe, just maybe, some patterns are designed, some timing is deliberate, some objects passing through our sky carry intent rather than just momentum. We don't know. We can't know, not yet, not with what we can currently observe and measure. But we can remain open to the possibility while avoiding the trap of certainty in either direction. If you believe the narrative about Atlas being just a comet, you might be right. You might also be missing the most important discovery in human history because you preferred comfort over discomfort, certainty over uncertainty, the known over the genuinely alien. If you believe the narrative about Atlas being something more, you might be right. You might also be pattern matching on noise, seeing design in randomness, constructing elaborate theories to explain data that has simpler explanations. The only intellectually honest position is doubt combined with attention. Doubt that we know enough to conclude definitively. Attention to what the universe is showing us, even when it's uncomfortable or ambiguous. The sky doesn't care what we believe about it. It just is. And we temporary observers with limited instruments and biased interpretations, do our best to read its messages written in light and gravity and the motion of objects across unimaginable distances. Look up. But also ask who wrote the schedule, if anyone did. Ask what you're leaving unseen while you watch what's most visible. Ask whether the narrative you've accepted is one you chose or one you were given. The cosmos is vast and strange and indifferent to human storytelling. But we're storytelling animals, and the stories we tell about what's above us shape how we understand what we are. So tell those stories carefully. Question them rigorously. And remember that the truest answer to cosmic mysteries might always be, at least for now, simply this: we don't know, but we're watching, and that watching itself is the beginning of wisdom.